So components of vector. What is the x component of A? So here's vector A. What part of A is in the x direction? So you don't even have to really do trig to do this one. You can just count how much of A is in the x direction. 1, 2, 3. What's the y component of A? 1, 2, 3. That's how much of A is in the y direction. Now just be careful with C. C is not here over at the origin. It doesn't start at the origin. But for the x part, you to go 1, 2, and that's in the negative direction. So negative 2 would be the x part of C. Actually, we want B, but okay, we'll go back to B. And then negative 1 in the y direction for C. Now for B, we've got 1, 2 in the x direction, and it's positive. 1, 2, 3, and it's negative 3 because we're going that way. Okay, so go through D and finish up C. Okay, and then same thing in ordered pair notation. What would vector B be? So this would be like the x part, comma, then the y part. Okay, good. Let's look at the next one. So this is about chapter 3, which is two-dimensional motion. So we have to be able to do a little bit with vectors here. A velocity vector 54 degrees above the positive x-axis has a y component of 15 meters per second. What is its x component? All right, let's take a look at this and then do a little review of trig. Okay, here's what we have. This is theta, 15 degrees, and we want to know how much the x part is. Okay, so remember the different sine, cosine, tangent. This one we could actually use tangent. So the tangent of theta, and you have probably a different theta than I had, so I'll just leave it as theta, is the x part, or sorry, the y part divided by, I should say, the opposite side. This is the opposite side divided by the adjacent side. Okay, and then a little bit of algebra here. Vx turns out to be 15 meters per second divided by the tangent of theta. Okay, so when I say a little bit of trig review, the tangent of theta, opposite over adjacent, let me just call this h for the hypotenuse. Now that we have the x part, we could get h if we wanted to. Let me just remind you what these different sines and cosines are. Sine of theta is the opposite side over h. So then you could get h that way if you wanted to. They don't ask for that in this problem. Cosine of theta is the adjacent side over the hypotenuse. Okay, so I just wanted to run through sine, cosine, and tangent. Okay, let's get back to the homework assignment. Okay, so this problem builds on what we did in the last problem. Part A, find the x component of vector d. So d is kind of like the hypotenuse, which is 120 meters, 65 degrees below the positive x-axis. So let me just kind of set up part A, and then I'll leave the rest of this to you. Okay, so here's the picture I have. This is theta, which they tell you is 65 degrees below the positive x-axis. Okay, the other ones might be above. This one is below. And then they tell you d is 120 meters, and we want to figure out the x part. Why don't I just call this d, sorry, this is actually the y part, dy and dx. Now you know dy is going to be negative, and you know dx is going to be positive from the picture. So here's how I like to do these, and you know what d is. So the sine of theta would be the opposite side, dy over the hypotenuse, and then the cosine theta would be the adjacent side, dx, d sub x, divided by d. And then you can get both of these. So d sine theta is dy, d cosine theta is equal to dx. Now when you do this, you put 120 sine of 65 to get dy. That's going to just come out to be positive. You have to then insert the negative sign because of the picture. Dx will also come out to be positive, and from the picture that you can see that it should be positive. So I know that dy is negative. I like to use these angles smaller than 90 degrees. There's a way of doing these problems where you can force this to come out to be negative, but you've got to consider larger angles than 90 degrees. So I'm just looking at this small triangle, figuring out the y part, and then I know I have to insert the negative sign from my picture. Okay, let's look at the next one. Okay, so the next one, you begin sliding down a 15-degree ski slope. Ignoring friction and air resistance, how fast will you be moving after 10 seconds? Okay, so this kind of builds on the kinematics equations that we saw from the previous chapter and takes into account looking at motion on a ramp. Okay, so let's set this up. Okay, so I'm just going to draw this as kind of a block sliding down an incline here. And the incline is 15 degrees. Now, you have to bring this to the problem. The initial speed is 0 because we just begin sliding from rest. So after 10 seconds, how fast are we going to be going? So with this, the acceleration due to gravity is straight down. There's a component of gravity this way and a component of gravity this way. So if this is theta, this turns out to be theta. And we're looking at motion like this. So refer back to the chapter, but this is the way we're looking at it. We're taking this two-dimensional problem where really this block is moving both in what we typically consider the x and y direction. When I translate the axis like this, now the motion is only in the x direction, just this way. So this component of the acceleration down the incline turns out to be g sine of theta. So doing a little bit of trig, that's how much we actually have. Now when theta is 90 degrees, then the acceleration is just free fall. Sine of 90 is 1. So when this theta is completely up like this, you're just in free fall. The smaller and smaller the angle becomes, the less and less the acceleration is. Okay, so we can figure out the acceleration. It's 9.8 meters per second squared times the sine of 15 degrees. That's how much the acceleration is. Okay, so let me actually put some numbers in for this one. 9.8 times the sine of 15. I'm in degree mode. 2.536, I'll just write. 2.536 meters per second squared. And then it becomes a problem like we had in the last chapter. Final velocity is equal to the initial velocity plus at. The part that's new is figuring out this acceleration here. And then the initial speed is 0, then you can figure out the final speed, right? Because you know the acceleration and the time. Okay, great. Let's look at the next one. So more motion on an incline. In the soapbox derby in figure 1, this picture here, young participants build non-motorized carts with very low friction wheels. Cars race by rolling down a hill, assuming that the track begins with a 51-foot long section tilted at 13 degrees below the horizontal. What is the maximum possible acceleration of a car? Okay, so again, we can figure out the acceleration like we did from the previous problem. And then part B, if the car starts from rest and undergoes the acceleration the full length, what is the final speed? Okay, good. So let's look at a picture of this, and I can give you some hints with this one. Okay, so they say the track is tilted at 13 degrees below the horizontal. So here's the horizontal, 13 degrees below the horizontal. That's how they phrase the problem. That's the same angle that we have here. So this is really the same thing as we had a car on a track. And we know the length of the track is just called L. Okay, so the acceleration down the incline, just like we did before, x and y, the acceleration is g sine of theta. When we have this situation, g is straight down. You have a component of g this way and a component of g this way. That's theta. Turns out to be g sine of theta. Okay, so whenever you have a motion on a ramp like this, if you know this angle, the acceleration is g sine theta. Okay, so you can get that. You have, you know what g is, 9.8. They give you the angle. Mine's 13 degrees. You might have a different number. You can get that acceleration. That's the first part. The second part is how fast are you going after you've gone 51 feet? 51 feet, perfectly good. It's just not an SI unit, so you'll have to convert this into meters. Okay, and then you want to know how fast you're going after you've gone whatever the distance this turns out to be. Okay, so we don't know how much time we have here. The one kinematics equation, if you remember, that does not have time in it is this one. Okay? Final velocity squared is equal to the initial velocity squared plus 2a delta x. The length here that they give you, that's what delta x actually is. So delta x is the same thing as the length. Okay, and so then we're starting from rest. 2 times the acceleration, which you get from the first part, times delta x is equal to the velocity squared. Then you have to take the square root of that. But make sure that you convert the distance into meters. Now there is another way of doing this problem. If you wanted to, let's see, will this one actually work? I'm trying to think if we could do this in another way. Yes, okay. So these are the other two kinematics equations that we have. You could use this equation here to figure out how long it takes to get down the track. Again, initial velocity 0. You can use this equation to figure out how long it takes to get down the track. And then you could use the first equation here to figure out what the final speed would be. Okay, so more than one way of doing this problem. Let's take a look at the next one. Okay, so for each of the motions described below, determine the sign, positive, negative, or 0, of the x component and the y component of velocity of an object at the time specified. For all the motions, the positive x-axis points to the right, and the y-axis and the positive y-axis points up. Okay, that's what we're used to. Alex, a mountaineer, must make it across a wide crevasse. Alex runs horizontally to the edge and successfully makes the leap to the other side, which is below the point from which he takes off, as shown in the picture. Okay, so it does something like this. Determine the algebraic sign of Alex's velocity at the instant he leaves the ground, at the edge. Okay, so when he leaves the ground, the velocity, which way is Alex going? And you can take a look at these available hints. If you do, that you don't lose any points for looking at these hints. That's the way I've set this up. Okay, so think about what Alex's velocity is the instant he leaves the ground. So let me give you my own hint before you click these hints. Now we're assuming Alex is running horizontally. We're not assuming that Alex jumps through the air like this. We're assuming the instant he leaves the ground here, he only has a horizontal velocity. So the velocity would be in the x direction positive, and in the y direction 0. Actually, I want to do this one for us. Because we're just assuming he's moving completely horizontal. Okay, and that's correct. Part B, determine the sign of the velocity the instant before he lands safely. So he's over here. I don't want to say too much to give that away. Okay, so I'll leave the rest of this to you. These all deal with velocities. Okay, excellent. Let's look at the next one. Whoops. A ball is thrown horizontally. Okay, so this is physics speak for it doesn't have a y velocity. It's only traveling in the x direction. So horizontally means only moving in the x direction. Thrown horizontally from a 10-meter high building with the speed of 6 meters per second. Here's a video tutor solution. You can go through this. The author has worked out a similar problem. How far from the base of the building does the ball hit the ground? And also you could hit here the review link here to review this section in the book. This is projectile motion. We're moving in two directions simultaneously, the x direction and the y direction. Let's take a look at this problem. Okay, so here's the picture. The velocity that we have is in the x direction. That's just the height here. It doesn't seem like we're given a lot of information. But remember, the initial velocity in the y direction is 0 because we're moving horizontally. The acceleration in the y direction, negative 9.8. Acceleration in the x direction, 0. So there's a lot more that we actually can bring to the problem here, these three pieces of information. So this L that they tell us down here is really like delta x. So when you are traveling with projectile motion, the x direction, all you have is this, delta x over the time, right? There is no acceleration in the x. This is all you have. For the y direction, you have all the kinematics equations. Velocity final in the y is equal to velocity initial in the y, acceleration in the y, times time. You have final velocity squared in the y is equal to initial velocity squared in the y, plus 2 acceleration y delta y. And then you also have delta y, initial velocity in the y, times time, plus 1/2 acceleration in the y times time squared. These are just the regular kinematics equations. And again, you know the acceleration in the y, negative 9.8. So whatever happens in the y direction also happens in the same amount of time in the x direction. It's time that ties the x motion and the y motion together. Okay, so going back to this problem, they're asking us for what delta x is. Well, delta x is the x velocity times time. That's what delta x is. That's perfectly great. We know the x velocity, we don't know the time. We can figure out the time from the y direction and then use that in the x direction motion. That's how these projectile motion problems always work out. We also know that this distance in the y direction is 10 meters. In terms of displacement, this is starting here and going here. The displacement in the y direction is actually negative 10 meters, right? Because in the y direction, you're going this way. You started up here, you end up on the ground. Okay, so we've got to sift through these three equations and figure out which one will give us the amount of time. So we know, again, we know delta y, we know the initial velocity in the y, we know the acceleration in the y. We don't know the y speed, the y velocity right before we hit the ground. Both of the first two have final velocity of the y involved. Let's see if the second one we can get the time from, the third one. Delta y, we know that. Initial velocity in the y is 0. That term would go away. 1/2 acceleration in the y times time squared. Good, so from the third equation we can actually figure out the amount of time. So the third equation that I have written, delta y, initial velocity in the y times time, plus 1/2 acceleration in the y times t squared. It's kind of cumbersome to keep writing y, subscript y, but I'm just really doing that to emphasize the difference between this is the y direction, this is the x direction. This term is 0, so 2 times delta y, so this is 0, multiply both sides by 2, divide by the acceleration in the y, square root of that will give you the amount of time. And then you need that amount of time up here to figure out how far we scoot over in the x direction. Now, if you forgot to put negative on the delta y here, you'll notice that, oh, well, how are you going to do this then if that's not negative? Because the acceleration in the y is negative. The negative sign actually cancels out, so that would probably clue you in on that part. Okay, let's look at the next one. Okay, a mountain lion running mountain lion can make a leap of 10 meters long, reaching a maximum height of 3 meters. What is the speed of the mountain lion as it leaves the ground, and at what angle does it leave the ground? Okay, good. So this is you leave at one level, come back to the same level. Let's take a look at this. Okay, so here's the picture. The mountain lion leaves with a certain speed. Now this is the overall speed. It's made up of the x part and the y part. Reaches a maximum height of 3 meters. We know at the maximum height the y velocity is 0, and then the total horizontal distance we travel is 10 meters. So we want the overall speed, and we want the angle that we leave at. So let me give you a better picture of what's going on here with this overall speed. It has a part in the x direction, which does not change the entire time, and it has a part in the y direction, which actually does change. You start off with some y value, and then the y velocity gets smaller and smaller and smaller until it's 0 here, and then it gets more and more negative on the way down. The x part does not change. We're assuming there's no air resistance. Okay, so one thing that we know about the maximum height, that's where the y speed is equal to 0. Okay, so there's several different ways of doing this problem. Again, the only thing that you have in the x direction is this distance. And there's no acceleration in the x direction. So the x direction, displacement divided by time. Good. So if you knew the time, you could figure out the x velocity. In the y direction, again, you have all of the kinematics equations. Velocity final in the y is equal to velocity initial in the y plus acceleration in the y times time. Again, acceleration in the y is negative 9.8 meters per second squared. I'll just do them all again here. Velocity final in the y squared is equal to velocity initial in the y squared plus 2 acceleration in the y times time squared. Actually, 1/2. Sorry, 1/2. No, that's right. Sorry, getting a little ahead of myself. Let me start over on that one. I'm mixing two equations together. Velocity final squared in the y is equal to velocity initial squared in the y plus 2a in the y times delta y. And then what I tried to say, delta y, initial velocity in the y times time plus 1/2 acceleration in the y t squared. This is all that we have to work with in the y direction. Okay, and this is an important fact here that at this point here, when the height is 3 meters, the y velocity is equal to 0. So again, there's several ways of doing this problem. We're not given a lot of information, so this is the trickiest problem that we've seen yet this semester. So looking at this and using this fact, we don't know the initial velocity in the y direction, but maybe we can find it from one of these equations. So it looks like this equation here, we could actually use this to figure out the initial velocity in the y direction if we look at the point from here to the highest point. So let's actually figure out the initial velocity in the y direction just going between here and here. Okay? Once I figure out the initial velocity in the y direction from this equation, then I can come back here to get the amount of time. Again, using where I started and the highest point, you figure out the amount of time, then I can get the x velocity. So let's take a look at this. Final velocity squared is equal to initial velocity squared plus 2 acceleration in the y delta y. So as I said before, final velocity doesn't mean at the end, it just means later than the earlier velocity. So I'm considering where I started here and the highest point. That's where the displacement in the y direction is 3 meters. Okay, and I'm using the fact that at the highest point, this is 0. So highest point, this is 0. I'll just throw in this step of algebra here. I still have the initial velocity in the y squared plus 2 acceleration in the y delta y. And then I've got to subtract this from both sides. So 2 acceleration in the y delta y. That's equal to the initial velocity in the y squared. And then you'll have to take the square root of both sides. So don't worry about that negative sign because you know the acceleration in the y is negative. So the negative signs cancel out. So you can use this to figure out the initial velocity in the y direction. That's the first thing you have to do. Okay, then we could use that to figure out how long it takes to get to the highest point. So let's use this equation to figure out the time it takes to get to the highest point. Okay, so that the highest point, the final velocity in the y is 0. Now we know the initial velocity in the y. You'll have to figure out what it is, but you know you can find it, plus acceleration in the y times time. So minus initial velocity in the y, which you got from the previous step, divided by the acceleration in the y, will give you the time. Now that's just the time to get to the highest point. You'll have to take this time and multiply it by 2. Maybe I should have called this like prime or something just to distinguish it from what I called time here. So 2 times this time is the entire time of flight, they call it. This is just the time to get to the peak. This is the entire time. Okay? And then once you have that time, again, I told you this is going to be a tricky problem. You could use this time here, this is really the third step, to figure out the x velocity. So why do you need the x velocity and the initial velocity in the y? Well, the overall velocity is the x part squared plus the initial part in the y squared. So you need both of those to figure out the overall velocity. This is theta, I'll leave it to you to get theta, but you'll have to use a little trig. You'll know this, you'll know this, you'll know that. You can get theta however you want to. Okay, good. So lots of work on this problem. It took a whole piece of paper, but it was definitely worth it. Okay, let's look at the next one. A rifle is aimed horizontally at a target 49 meters away. The bullet hits the target 1.9 centimeters below the aim point. And again, you can take a look at the video tutor solution here. So if you fire a rifle horizontally, as soon as the bullet leaves the rifle, it starts going lower and lower and lower in the Y direction. If you take a dart and you aim it right at the bullseye, and it travels horizontally at the bullseye, you'll never hit the bullseye. It's always going to start sinking immediately. Now your brain compensates for this if you're playing darts. You have to loft it up, and then it comes back down and hits the bullseye. Okay, so let's take a look at this one. Okay, so here's 49 meters away. You might have different numbers, so really that's what the displacement is in the x direction. Now the bullet, if you aimed it horizontally, it's not going to go across there. It's always going to drop some. So they tell you it drops 1.9 centimeters, so the displacement in the y, negative. And in meters, 0.019 meters. You've got to divide that by 100. Okay, it doesn't look like we have a lot of information here, but we also know the acceleration in the x is negative 9.8. It's fired horizontally, so we know the initial speed in the y direction is 0. Okay, now to get this x velocity, that's the second part, we need the displacement divided by the time in the x direction. They give you the displacement in the x, we have got to use the time from the first part. So we could use the y direction to figure out the amount of time. I wrote the kinematics equation several different times. Let me see if I can come up with one. Maybe this one will work. Let's just try it and see. The displacement in the y, initial velocity in the y, times time plus 1/2 acceleration in the y times t squared. This is how it goes. You look at one equation. Is this going to work out for us? Okay, we know the displacement in the y. The initial velocity in the y is 0. That term's actually 0. 1/2 a t squared. This one will actually work for us. We can figure out the time from this equation. We can't figure out the time from this one because we don't know the y speed right before it hits the target. We don't know this. It's not 0, that's after it hits the target. You need the speed right before it hits the target. Okay, so this one won't work for us. That's why I'm not using it. Okay, so 2 delta y, so this term is 0, multiply both sides by 2, divide by the acceleration in the y, the square root of that will give you the amount of time. Okay, so we use the y direction to figure out the amount of time. That's part A, and then use that time in this equation to figure out the initial velocity, which is really the x velocity. All right, on to the next one. Okay, Apollo 14 mission to the moon. Alan Shepard hit a golf ball with a golf club improvised from a tool. The free fall acceleration on the moon is 1/6 of the Earth. So take 9.8, divide it by 6 to get the magnitude. Suppose he hit the ball with the speed of 29 meters per second at an angle of 26. How long was the ball in flight, and how far did it travel? And then ignoring air resistance, how much farther would it have traveled on the moon than the Earth? So we'll take the moon distance divided by the Earth distance. Okay, so we'll use something called the range equation to solve this problem. Let's take a look at it. Okay, so this is the range equation. First of all, here's the picture. The overall speed is given, the angle is given. Now the range equation is only going to work for this situation, where you leave at one level and come back down to the same level. So the range is the overall velocity squared times the sine of 2 times theta divided by g. So it's actually easier to get part B in this problem. You're given the overall speed. I'll just leave that like this. Overall speed. You're given the overall speed. That's what 29 is. Sine of 2 times theta. So the sine of 52 degrees divided by g. So I'll put g in quotes here. Remember, you've got to figure out what g is. It's 9.8 meters per second squared divided by 6. Okay, so do part B first to get the range. And then the time of flight, how are you going to get that? Several different ways of getting that. I would say probably the easiest way is this. X velocity is the range divided by the time. Remember, the range is the x distance. So the time would be the range divided by the x velocity. Now this is not the x velocity, this is the overall velocity. The x velocity is the overall velocity times the cosine theta. You don't need it for this problem, but the y, well, you might depending on how you do the problem. The initial velocity in the y is equal to v sine of theta. Okay, good. So you can figure out the range, you will figure out the range here. You can figure out the range on the Earth using the Earth g, and then part C, subtract those distances. Okay, so range equation, very beneficial, only good for this specific situation when you leave at one level and come back down to the same level. By the way, you can see what the maximum range would be. The sine of 90 is when the sine function is a maximum, so theta would have to be 45. So that probably goes along with your intuition that the maximum range turns out to be from 45 degrees. Okay. Okay, so let's see what we have here. The very last problem. One of the longest recorded passes in an NFL game traveled 76 yards. Okay, yards perfectly good, but you're going to need to convert that into meters. Assuming that the pass was thrown at an angle of 45 degrees, what was the speed at which the ball left the quarterback's hand? Okay, so you can use the range equation for this. You're given 45 degrees. You're given the range, 76 yards. You'll need to convert that to meters. So you're given the range and the angle, and it's on Earth, so you know G is 9.8 meters per second squared. You'll have to figure out what the speed would be. So use the range equation like we did on the previous problem. Instead of finding the range, though, the range is given, find out what the speed would have to be. That's the quickest way of doing this. Other ways of doing it, but the range equation really helps out with this problem. Any questions, just send me an email and I'll talk to you soon.